Hey everyone. So in today's class, we are going to start with unsupervised learning. Let's first revise the difference between supervised learning and unsupervised learning. So in machine learning, we have three types of algorithms. One are called supervised learning algorithms, the other are called unsupervised learning algorithms, and the next category is reinforcement learning. So in supervised learning, what we do is we work with the label data. That is, we have some independent attributes and we have one target attribute that we would like to predict. And in supervised learning, there are multiple categories, two major ones, which are classification and regression. In classification, our target is basically categorical, whereas in regression, our target is continuous. In unsupervised learning, we basically work with unlabeled data. What does unlabeled data means? Unlabeled data means that we don't have any target that we're trying to predict. We just have a set of independent attributes. Now, there are multiple algorithms in unsupervised learning. One of them is clustering, which we are going to study now. Then the next one is PCA, which we are going to study in the next classes. And there are others also like association rule mining and so on. So there are multiple algorithms. We are going to focus on clustering and PCA. And in today's class, we are going to study clustering. What is reinforcement learning? Reinforcement learning essentially means that we have an agent which is trying to interact with the environment, trying to maximize its rewards and minimize its punishments. Okay, so today we start off with clustering. So in clustering, what do we have? Let's say we have, let's take the data set that we already have seen. It's gender, SSCP, SSCB, HSCP, HSCD, and so on, right? And there are a lot of things. So basically, in clustering, what are we trying to do is, let's say we have 10,000 students. We are basically trying to divide these 10,000 students into three batches or four batches. That is, the similar students should be in one batch, and the students which are not similar to one another, they should be in different batches. Why should we do this? One of the example could be, let's say there are 10,000 students and I want to make a placement program for them. Now, obviously, one placement program might not cater to all the students because all students are different. And since all students are different, it also is obviously not feasible that I make 10,000 placement programs. No. So what I will do is I'll try to bucket them into three categories or four categories. For example, let's say four categories. So we are trying to bucket them into four categories such that similar students go in one group and dissimilar students go in different groups. That's what clustering does. It makes clusters. And based on these features, we are going to evaluate the similarity. Okay. So first of all, let's talk about Euclidean distance. Okay. Euclidean distance. Now, what is this Euclidean distance? Euclidean distance essentially means that you find the distance between 2 points. Let's say this is the point and this is the point. So for this point, feature 1 value is 6, feature 2 value is 2, and the feature 3 value is 3. And here also we have three features. We are taking only three features into consideration. And this is 1, this is 2, and this is 0. Okay. So what would be the Euclidean distance? Can you tell me? So Euclidean distance is basically the distance between 2 points in Euclidean space. And it's basically this length. That is the length of the line between the 2 points. And obviously this, since here we have three dimensions, it cannot be drawn in a plane properly. But if there are 4 dimensions, 5 dimensions, 6 dimensions, the formula is just going to remain the same. So what do? We basically have the formula as take the first feature, subtract the two values and square it. Similarly, take the next feature, subtract the values and square it. And take the next feature, subtract the values and square it. And then sum all of them and finally take the under root of that. If you have more features, then you're going to keep on putting it inside the under root. W1 minus W2 square plus P1 minus P2 square and so on. Okay. Now, let's see. So, it would be 6, x1 is 6, minus x2, which is 1. Then y1 is 2, minus y2, which is again 2. And z1 is 3 and z2 is 0. So what would be the Euclidean distance? It is going to be 5 square plus 0 square plus 3 square. So it's going to be 25 plus 0 plus 9, which is basically root 34. So the distance between these 2 points is root 34. So what we are trying to do is we are trying to put similar points in same group and dissimilar points in different groups. And how are we going to find the similarity or the dissimilarity? We are going to basically find the Euclidean distance between the points. If we have, let's say, gender SSCP, SSCB, HSCP, and HSCB, that is, there are 5 points. So there are 5 features. So basically the formula would look like, let me write it as gender 1 minus gender 2 whole square plus SSCP 1 minus SSCP 2 whole square plus HSC first SSCB. SSCB 1 minus SSCB 2 whole square plus HSCP 1 minus HSCP 2 whole square plus HSCB 1 minus HSCB 2 whole square. So this is what you have to do, and this is all under the under root. So this is how you find the similarity or the distance between the 2 points. If the distance is more, that means the 2 points are far away from each other, that is they are dissimilar. So let's see. So what is the main principle of clustering? The points which are in the same cluster, they should be similar to each other. That is the intra-cluster distance. That is the distance between 2 points in the same cluster. It should be minimized. That's what intra-cluster distance means. That is the distance between 2 points in the same cluster. And since they are in the same cluster, the distance should be less. So the intra-cluster distance should be minimized. Now, what is meant by intercluster distance? Intercluster distance means 2 points. 2 points which are in 2 different clusters. 2 points which are in 2 different clusters, their distance, it should be maximized because they are in 2 different clusters, that is, their 2 are different, so their distance should be maximized. So the intra-cluster distance, that is distance between 2 points in the same cluster, is minimized, whereas intercluster distance, that is the distance between 2 points in 2 different clusters, is maximized. Okay, that's what is the main principle of clustering, and no matter what clustering we do, the main principle remains the same. That is the intra-cluster distance is minimized and the intercluster distance is maximized. Now, the notion of cluster can be ambiguous. Let's see. Let's see this example and figure out how many clusters are there. What do you think? How many clusters would be there? One thing that will come normally to you, or probably it's intuitive, is that this is one cluster and this is another cluster. So yes, we can have 2 clusters. But it's totally fine if we have 4 clusters also. One this, one this, one this, and one this. And then we can have 6 clusters also. So if you see how many points are there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So in total, there are 20 points. So what is the minimum number of clusters that you can have? The minimum number of clusters would be 1, where all these points are in just one cluster. So the minimum number of clusters that you can have is 1. And what is the maximum number of clusters? The maximum number of clusters is equals to the number of data points that you have. Why? Because each point can have its own cluster. No 2 points will be in one same cluster. All the points will have their own cluster. So the maximum number of clusters that we can have is 20, since the number of data points here are 20. So the number of clusters could be from 1 to the number of data points. It could be any value in between. So that's why we say the notion of cluster is ambiguous. We can have 2 clusters, we can have 3 clusters, we can have 4 clusters, and so on. Now, there are 2 two types of clustering. So first of all, we know what clustering is now. Clustering is basically an unsupervised learning technique in which we are trying to group data points. Okay. And what's the main principle? That is the intra-cluster distance should be minimized and the inter-cluster distance should be maximized. Now there are two types of clustering techniques that we have. Let me show it here. Yes. One is called partitional clustering and the other is called hierarchical clustering. So what is partitional clustering? In partitional clustering, one data point will belong to only one cluster. So clustering data points into non-overlapping subsets such that each data object is exactly in one cluster is called partitional clustering, the one that we already saw. Let's see these examples. So basically, if you divide it into two clusters like this, then if you see each data point, each data point belongs to one cluster only. Here also this data point is a part of this cluster, this data point is a part of this cluster. So each data point is belonging to only and only one cluster. Moving on to the next category, which is hierarchical clustering. In hierarchical clustering, what happens is we don't have each data point belonging to only one cluster. Let me show it to you. Let's say these are the points. Like this. So basically what happens is some points are in one cluster. Over it, we have another cluster. Then let's say it like this and like this. So if you see in this way, one point can belong to multiple clusters. For example, if you see this point, it belongs to this cluster and it belongs to the bigger cluster also. If you see this point, it belongs to this, it belongs to this, and it belongs to this cluster as well. So here one point can belong to different clusters. This is not very intuitive, but it has a lot of applications. I'll explain you what. So first of all, summarizing this in hierarchical clustering, we have data objects into set of nested clusters and it kind of forms a tree. So let's see an example. Let's say basically uh, there is one person. So basically we are actually having a social networking website and there's one person from Delhi. I'm only taking the location into consideration. Okay, that is only one feature. There could be multiple features. Then another person is from Bhopal. The next person is from Jaipur. The next person is from Bangalore. The next person is from Hyderabad. So let's say there are five people. So if you see people from Delhi, Bhopal and Jaipur. These are locations in the north, right? This is center. These are the locations in north. So Delhi and Jaipur are very close to each other. So if you have a social networking site, then people which are close to each other or people which are similar, they will be first categorized in one group. So a person from Delhi will get the first suggestion of the friend as from Jaipur. Similarly, Bangalore and Hyderabad are close to each other, so the person from Bangalore would probably get a friend suggestion for the person in Hyderabad. Now, this is about the first suggestion. Now, Bhopal is also close, right? So, what will happen is this will be combined with Bhopal. This cluster will be combined with Bhopal. So basically, after the person from Delhi has got the suggestion from for the person in Jaipur, now he'll get the suggestion for the person in Bhopal. Now these three become the cluster, which is the north cluster, and this becomes the south cluster. And then what happens is now since all of them are part of India, so they will be combined and they will make a bigger cluster. That is now if the first person got the first person in Delhi got the suggestion for the friend from Jaipur, then the second friend suggestion he's going to get from Bhopal and then he's going to get from Bangalore and Hyderabad because they are the part of the same country. So basically first Delhi and Jaipur get combined, right? Then we can combine Bangalore and Hyderabad. Then Delhi Jaipur cluster gets combined with Bhopal cluster. And then finally, all get combined into a big cluster, India cluster. So if you see, Delhi is basically a part of this cluster, it's a part of this cluster, and it's a part of this cluster also. So that is what hierarchical clustering is, where one point can be a part of multiple clusters. And hierarchical clustering is generally used in social networking sites. Okay, so that's what's the difference between hierarchical clustering and partitional clustering. Okay, so now the main clustering that we are going to learn is basically partitional clustering, but we'll take a feel of hierarchical clustering also with the help of an example. Okay, and in partitional clustering, we are going to talk about k-means clustering. So let's quickly revise what partitional and hierarchical clustering is. In partitional clustering, there is only one data point. One data point will belong to only one cluster, whereas in hierarchical clustering, it is not the case. One point can belong to multiple nested clusters. Okay, and hierarchical clustering is the most popular and widely used method to analyze social network data. In this method, what happens is the nodes are compared with one another based on their similarity, and larger groups are built by joining groups of nodes based on their similarity. Okay, let's move ahead to the first one, which is partitional clustering. And in partitional clustering, we are going to talk about k-means clustering. Okay, that's the main algorithm that we are going to talk about, and we are going to write the code for it also in the coming classes. So let's see. So in k-means clustering, what happens is, let's understand this with the help of an example. We have 8 points and we want to create some clusters. Now here k-means, where in k-means, k stands for the number of clusters. Let's right now take the number of clusters to be 2. Okay. So we have 8 points and we want to apply k-means clustering, and the number of data points that we want are, a number of clusters that we want are 2. What are the maximum number of clusters that you can make? Since there are 8 points, the maximum number of clusters that you can make is 8. And what are the minimum number of clusters? Minimum number of clusters are going to be 1. So the minimum number of clusters are 1 and maximum is 8. But for now, we are taking k is equals to 2. You can take it to be anything. K is equals to 1, k is equals to 2, k is equals to 3, 4, 5, 6, 7, 8. Now, one more thing. Is k is equals to 1 going to actually help you with anything? No, it is not going to, because putting all the students in one batch, it's simple to not doing anything, right? If you're not grouping them, then you're not doing anything. You're just putting all of them together, and in that case, you don't have to do any clustering. You just can put all of them together in one bucket. So k is equals to 1 does not do any help to us. It's not grouping anything. Okay, so back to k-means clustering. In k-means clustering, we have right now 8 points and we are going to have 2 clusters. So the first step was to choose the number of clusters k, and we have chosen it to be 2. You can choose it to be 3, 4, anything. Then the second step is basically select k random points from the data as centroids. So basically now what you have is 8 points, right? Out of these 8 points, since you need 2 clusters, you randomly pick 2 points as the centroid. Now the question would be, what is the centroid? What is centroid? Centroid is basically the center of a geometric object. It's basically the center. So basically, centroids means that we are finding the center points for the clusters. And essentially, we can randomly pick any 2 centroids initially. Any 2 centroids can be picked out of these 8 points. So any 2 points you take and you call them as centroids. So this is basically the centroid of the red cluster, and this is the centroid of the green cluster. Okay, so this is the second step that we do. Now what we will do is, in the third step, we will find the Euclidean distance We already know what Euclidean distance is. We already discussed that. So now what we'll do is we'll find the Euclidean distance each point, of each point from both the centroids. So this is some distance and this is some distance. Now, if let's say this distance is 4 and this distance is 2, then which centroid or which cluster this point should go to? Since the distance of this point is less as with respect to centroid 2, then it's closer to centroid 2. That means it should go to green cluster. If you talk about this point, let's say this distance is the distance of this point with C1 is, let's say, 1, and the distance of this point with C2 is, let's say, 5. So what you have to see is that this point is closer to C1. So it will go to red cluster. So now, based on the Euclidean distance, you assign all the points to the closest cluster centroid. You see the distance of a point from both the centroids, and whichever is minimum, you assign the point to that particular cluster. So these points are closer to C1, so that's why they are red. These points are closer to C2, that's why they are red. This point, if you see, it is closer to C1 as compared to C2, so that's why this point is also red. So what are the first three steps? First step is assign the K value, figure out what your K needs to be. Obviously, we'll understand a way in which we can figure out which is the optimal value of K also, which is called the elbow method. We are going to do it in some time. The second step is to basically randomly pick K centroids. And third is to assign all the points to the closest cluster centroid. Now, this was one iteration. So this was one iteration. That means you chose the centroids randomly, and then to each point, you put it into one particular cluster based on the Euclidean distance. This was one iteration. You have to do this again and again. So again, what you will do is, now you already have the clusters with you, but you want to ensure that all the points go to their right clusters. We can't ensure that in one iteration because we randomly picked the centroids. If you would have picked this as C1 and this as C2, then the clusters would have been different, right? So we have to do multiple iterations so that we reach the position where we get right clusters. Okay. So now what you're going to do is recompute the centroids of the newly formed clusters. How do we do that? So let's see if we have this point, this point, this point, this point in one, and this point in one cluster, and the other cluster is this. Let me just randomly put the points, that is the coordinates. So we have, let's say, two features. For feature 1, the value for this point is 1. For feature 2, it's 2. For the next one, it's 0, 4, then 0, 3, 5, 2, 1, 0. Okay. For this, it's 0, 0, 2, 3, and 1, 5. So how do you find the centroid of this cluster? So what you do is basically take the average x coordinate and average y coordinate. That is, basically take the average value of all the first attributes and average value of the second attribute. So basically we'll have 1 plus 0 plus 0 plus 5 plus 1. So it is 7. 7 by 5. Okay. And for the y coordinates, it is 2 plus 4 plus 3 plus 0. 2 plus 2 plus 4 plus 3 plus 0, which is 11 by 5. Okay. So this is basically the centroid that you have, 1.4 and 2.2. Okay. Similarly, you do it for the second cluster also, which for the x coordinate, it would be 0 plus 2 plus 1 by 3, that is 3 by 3. And for the next one, it will be 0 plus 3 plus 5 by 3, which is 8 by 3. So it's going to be 1 by 1 comma 2.66, like this. Okay. So basically, once we have the clusters with us, we have to find the new centroids. Initially, you took random centroids, but now you can take the centroids by finding the um, actual centroid from the cluster points. Okay. Now, once you have the new centroids available to you, again you do the same thing. The same thing is what? The same thing is that you have to check for each point the distance of that point from the centroid of red cluster and the centroid of green cluster, and see this point is closer to which cluster. This point is closer to which cluster centroid, and wherever it is closer. Now, if you see, this distance is lesser as compared to this distance. So now this red point will actually become a part of the green cluster because its distance from the green cluster centroid is less. This point will remain in green cluster because this distance is less. This will also remain in green cluster. This will also remain in green cluster. This point will be in red cluster only because this distance is more and this distance is less. Similarly, all these points are closer to the red cluster centroid, so that's why they will remain in red cluster only. So now we have these 4 points in red cluster and these 4 points in green cluster. Only this point changed the cluster. Why? Because here this distance is less as compared to this distance. So now we have got new clusters. This is the second iteration. Now in the third iteration, what you will do, you will find out the centroid, and then again you're going to figure out points belong to which cluster. In the next iteration, what you will do, again find the centroid and then figure out points belong to which cluster, and based on the Euclidean distance just put them into the clusters. And you will continue doing this, and eventually you will get the right clusters. We started with this, right? We started with this cluster and this cluster, but eventually we reach the right clusters. Okay, so this can be done for any value of k. Now the question is, when do you stop? When can you stop doing these iterations? You have to do multiple iterations. When should you actually stop? So you should stop when one of the three conditions is met. So the conditions are: first, the centroid of a newly formed cluster does not change. So here, let's say we have some centroid here, and let's say we have some centroid here. Then again, we figure out the points are belonging to which cluster, and based on that, make the clusters and then figure out the centroids again. If in the two subsequent iterations, the centroids don't change, then you can stop. That means nothing is happening. The centroids are not changing. Okay. Second is points remain in the same cluster. That is, if in this iteration the clusters are this and this, and in the next iteration also the points remain in the same cluster. Here, if you see, this point actually changed its cluster in the next iteration. But if in subsequent iterations there's no change happening for any point, then in that case you can also stop doing clustering. And the third one, which is generally followed, is say that I am going to do 100 iterations, and whatever answer I get after 100 iterations is going to be my final clusters. So you can use any of these stopping conditions. So centroids of the newly formed clusters do not change can be one stopping criteria. Points remain in the same cluster can be second, and the maximum number of iterations are reached. For example, we set the maximum number of iterations to be 100 or 200. Okay. So that is pretty much all about clustering. Here we don't have any training data. Here we don't have any testing data because we are not trying to predict anything. We just take the data that we have and build the model out of it. And what's the model? That all the points, they get segregated into groups. That's what clustering is. Now, how can we evaluate this model's performance? How can we do that? We can do that using R square or adjusted R square or MSC or RMSC. Can we do that? Or using accuracy or precision or recall? No, we cannot, because again here we don't have testing and testing data and the predictions that we get. No, here we don't have labeled data, so we cannot use those evaluation metrics. So here we have separate evaluation metrics. One of the most common ones is called inertia, and we will understand what inertia is. Let me help you with the concept with an example. So inertia basically calculates the sum of square of distances of all the points within a cluster from the centroid of that cluster. So let me take some points. This is one point. This is next. This is next. This is next. So this is one cluster and the centroid lies here. Let me make another cluster and the centroid lies here. Okay, now let me just put the coordinates. Again, we are taking only two features, x and y. Those are two features, or you can say f1 and f2, and just put their coordinates like this. And here, just putting random numbers. Don't, okay, let me just change it like this. These are random coordinates that I'm putting. They will actually be something. I'm just putting random numbers to explain you the concept. So what is inertia? Inertia basically calculates the sum of square of distances of all the points within a cluster from the centroid of that cluster. So basically you find out this distance. What is this distance? It's 2 minus 1 square, which is 1. Then 4 minus 3 square, which is 1. So basically this distance is root 2. Then find out this distance. So 1 minus 1 is 0 and 2 minus 3 is minus 1 square, which is 1. Under root 1 is 1. Then what is this distance? This distance will be 1 minus 1, again 0, and 0 minus 3, which is 3. 3 square is 9, and take the under root of that. So it's 3. What is this? So it's going to be under root of 1 plus 4, which is root 5. Okay, let's talk about this distance also. So 12 minus 2 is 10, and 1 minus 12 is minus 11. So basically 10 square plus 11 square. So it's going to be 11 square is 121, and 10 square is 100. So it's going to be root 221. I'm just calculating the Euclidean distance. And then here it would be 13 minus 2 square plus 2 minus 12 square. Okay, so it's going to be 11 square plus 10 square. So again, it's going to be root 221. Then what about this? It's 11 minus 2, which is 9 square, plus 5 minus 12, which is minus 7 square. So it's 49. So it's 81 plus 49. So under root 130. Okay, so basically what do we do here is we figure out the distance of each point from its centroid and then square the distances. So basically we have to take all these distances. So 1, we have to square it. 1 square plus root 2 square plus 3 square, which is 9, plus root 5 square, which is 5. So we have to take the sum of the square of distances of all the points from their centroids in one cluster. Okay. So what we are doing is we are squaring the distance of the point from its centroid and summing it up. So we are taking the distance of the point from its centroid. First, we are doing the square of it and then summing it up. So sum of square of intra-cluster distance, or sum of square of distance of all the points within a cluster from the centroid of that cluster. So you take the distances of the points from the centroid, square them up, and then sum it over. Okay, that is sum of square of intra-cluster distance for one cluster. You do the same for the next one also. So let's say this comes out to be I1, this comes out to be I2. Now the total inertia will be the sum of all the inertias of all clusters. So we calculate this sum of square of intra-cluster distance for all the clusters, and the final inertia will be the sum of intra-cluster distance of all the clusters. You sum up all the inertias, I1, I2, and so on. That's what inertia is. So inertia for one cluster is going to be sum of square of distance of all the points within a cluster from the centroid of that cluster, and the final inertia will be the sum of all the inertia of all the clusters. Now, the next question is, should inertia be less or high? Inertia is basically the sum of square of intra-cluster distance for all clusters, right? So the distance of the point from its cluster centroid, it should be less. So the inertia should be less. If you have a good clustering, then your inertia will be less. So the distance between the points within the cluster should be as low as possible. And keeping in mind this thing, we say that lesser the inertia value, better our clusters are. So inertia should be low. Okay, inertia should be low. Now, there is kind of a trade-off. We want our inertia to be low, and when will the inertia be the lowest? Inertia will be minimum when the number of clusters are the maximum, right? Because if each point belongs to its own cluster, then if let's say I had this as one cluster, another cluster, another here, here, and here, then since there's only one point inside the cluster, so that point will be the centroid itself. So the sum of square of intra-cluster distance for all the clusters is going to be zero. So the total inertia will be zero. So inertia will be minimum when the number of clusters is maximum, right? But obviously number of clusters as maximum, it does not have any relevance to us because making 8 clusters is actually doing nothing. And also there's one more thing. If the number of clusters are more, then what happens is the computations are more. Why? Because when if there are, let's say, 6 clusters here, if let's say there are 6 clusters, then you have to find out the distance of each point from the 6 centroids. If there are 10 clusters, you have to find the distance of each point from 10 centroids in each iteration and figure out which is the minimum and then assign it to that particular cluster. So you have to find this distance of each point from all the centroid clusters in every iteration. So basically, if the number of clusters are more, the number of computations are more. So we want our inertia to be minimum, but we don't want our computations to also be more. So we have to do a trade-off between inertia and the complexity of our algorithm. Our complexity should be less, that is the number of clusters should be less, but our inertia should also be less. So we want inertia to be minimum, computations to be minimum. So we have to have a right balance of the number of clusters. So if inertia is minimum, the number of clusters are more. We want our computations to be minimum. For that, we want the number of clusters to be less. So at one place, more clusters are desirable. At one place, less clusters are desirable. So we have to do a trade-off such that the number of clusters are optimal, such that inertia is also less and computations or complexity of our algorithm is also less. So that's what we do, which is basically the elbow method. So basically, this helps us figure out the right value of the k, right value of the number of clusters. Okay. So in this, what do you do is you basically take all the k values, you take all the k values or all the number of cluster values, or if not all, then take some of them and try to draw a graph between inertia and number of clusters. So you draw a graph like this, and the graph somehow comes to be like this. So let me draw it a bit more properly. Like this. So it's like a elbow. That's why the name is given as elbow method. So basically what happens is initially when you when you increase the number of clusters, let's say here we had some clusters and then you decrease the number of clusters. So if you see, if you increase the number of clusters, if you see the inertia that decreases is a lot. And then further, if you increase the number of clusters, again the inertia that decreases is a lot. So basically with increase in number of clusters, we are able to reduce lot of inertia. But if you come here, if you slowly come here, and obviously if you go to the right further, the number of clusters are going to increase, but you are not going to get significant decrease in inertia. If you see here, the number of clusters have increased, but the difference in inertia that you get is very less. This might be, let's say, 3, this might be 2. So the difference that you get in the inertia is going to be very, very less. So it's of no point to get so less decrease in inertia by increasing the number of clusters, because at the end, if we are increasing the number of clusters, we are increasing the complexity. So that's why we take a point at the elbow, so that the inertia is also less and the number of clusters are also less. So this is the optimum K value that you have to take. And now you can use this K value to actually do the clustering. This is the right value of K. Make sense? So that's how we figure out our K. And that's how we figure out what is the that needs to be used in K means clustering. That's all about partitional clustering. We'll understand the next clustering also. So again, there are lots of clustering techniques. In partitional clustering, we did one, which is K-means clustering. And in hierarchical clustering, we will do one, which is called agglomerative clustering. We'll just understand it so that we get a feel of what does this clustering look like. Okay. So let's say we have these data points. So what is agglomerative clustering? Agglomerative clustering is a bottom-up clustering. That is, you start off with six clusters. You start off with six clusters, but then you slowly move, you reduce the number of clusters, and finally you get one cluster. Okay? So that's what happens in hierarchical, in agglomerative clustering. Okay? So in hierarchical clustering, there are multiple categories. We are understanding agglomerative, and agglomerative, what happens is it's a bottom-up clustering in which we start off with um, n number of clusters. That is, the number of clusters is equals to the number of data points. And then what do we do is, then we are going to slowly reduce the number of clusters and then make only one cluster. Let's see how. Okay. So these are our 6 points, right? And we know the coordinates also. We are only taking two features into consideration, which is x1 and x2. If you want, you can take multiple features into consideration. Why I'm just taking x1 and x2? Because it's easy to draw it uh, on these coordinates, right? It's easy to draw it on the 2D plane. So we have these points, right? Now, what do you do is you find out a data matrix, that is, you find the distance matrix. So in this, what happens is you find out the distance of all the points with all the other points. So basically, this is A with A, that is the distance of A with respect to A. Then A to B, you find out the distance using Euclidean formula. Then you find the distance of A to C. Then you find the distance of A to D. Then you find the distance of A to E. Then you find the distance of A to F, and so on. Similarly, you do it for B to C, B to D, and so on. The distance of A to B and the distance of B to A will remain the same. So you don't have to calculate it again. Okay. Now, once we have this data or distance matrix, that is, we have the distance of each point with respect to other point, then what do? We find the minimum distance. Obviously, we don't have to include these diagonal terms because they are zero, and they essentially represent the same point. That is the distance of A with respect to A. That is, distance of A from A will always be zero. So we don't have to take that. But apart from that, try to take the minimum distance. Minimum distance means more similarity. So try to take the minimum distance. And if you see, zero point 0.5 is the minimum distance that we have. Okay, zero point 0.5 is the minimum distance. So D and F are the closest to each other, and that's why they can be combined into one cluster. So if you combine DF into one cluster, if you combine DF into one cluster, now you will have five clusters left: A, B, C, DF, and E, right? Now, the question would come, obviously, the distance of A to B will not change. A to C will also not change. But the distance of A with DF cluster will change. Now, there are multiple techniques of finding the distance of a particular point from the new cluster that we have got. There are different linkages that we have. Okay. So, I can explain you in simple terms. So what do? Is there are multiple techniques, right? You find the distance of A with D, which is 3.61, and then you find the distance of A with respect to F, which is 3.2. What you can do is you can take the average of these two distances, that is 3.61 plus 3.2 by 2, which is going to be 6.81 by 2. Or what you could do is you take the maximum distance between these two, that is 3.61. Or what you do is you take the minimum, which is 3.2. That's what you do. Single link basically means you link two clusters based on the minimum distance between the two elements. In single link, what we do is we take the minimum distance. The minimum distance is 3.2, right? So we take that minimum distance. So there are multiple linkages. One is single linkage. In single linkage, you take the minimum out of the two distances. In complete linkage, you take the maximum distance out of the two. And in average, you actually do the average of the two distances. Okay. So here, let's take the example of single linkage. So in that, what do? We have the distance 3.61 and we have 3.2. So you take the minimum of the two distances, which is 3.2. So the distance of A with the DF cluster will be 3.2. So out of these two distances, you're just taking the minimum, which is 3.2. Now, similarly, you do it for B cluster also. So you find out the distance of B with DF cluster. You take the two distances. The distance of B with D is 2.92 and the distance of B with F is 2.5. So you take the minimum out of these, which is basically 2.5. Okay. Now, for C. Now C and D distance is 2.24 and C and F distance is 2.5. So you take the minimum out of them, which is 2.4, 2.24. So here you put 2.24. Similarly, the same values will come here also. Now, if you see the distance of DF cluster with E, so what you do is find the distance of E with D, which is 1, and find the distance of E with F, which is 1.12, and take the minimum out of them, which is 1. And the technique that we are using here is single linkage. So this is how you make the matrix. So you take the minimum distances of this combined cluster. You take the minimum distances of all the other clusters from this combined cluster. Okay. And that is what single linkage is. You could use other linkages also, which are complete linkage or average linkage. Now we have this. Now we need to figure out again what is the minimum distance. Now we have 5 clusters. Now we want to bring these 5 clusters to 4 clusters. Okay. So check for the minimum. Obviously, zeros are not included. So the minimum that we get is 0.71. So in the first step, we combine DF cluster. In the second step, we are going to combine AB cluster. So now what we will have is this is one cluster, this is another cluster, E is the third cluster, and C is the fourth cluster. So we basically have 4 clusters in place with us. Now again, we are going to do the same thing. Find out the distances. So distance of AB with AB is 0. Now what is the distance of AB cluster with C? So find out the distance of A with C, which is 5.66, and then find the distance of B with C, which is 4.95. So which is minimum out of them? It is 4.95. So the distance of AB cluster with C cluster is going to be 4.95. Then what's the distance of AB with DF? Now for that you can take the previous one. Don't take the initial one. Take the previous data matrix only. Okay, data matrix or distance matrix. So basically find the distance of A with DF cluster, which is 3.2, and find the distance of B with DF cluster, which is 2.5, which is minimum 2.5. So that's why the answer is going to be 2.5. Now we check for AB cluster and E cluster. Distance of A with E is 4.24, distance of B with E is 3.54, which is minimum out of them. It is 3.54. So 3.54 is going to come here. Similarly, you fill up the entire distance matrix. Now, again, what do? You find out the minimum here. So first you've combined your DF, then you have combined your AB. Now it's your time to combine other it's time to convert 4 clusters to 3 clusters. So find the minimum. The minimum I see is 1, right? So 1 is the minimum. So now the next step would be to combine DF cluster with E. So now first you combine DF, then you combine AB, and now you're combining E with the DF cluster. So now we'll be remaining with three clusters. Now how do you find these distances? So AB with DF E cluster, what will be that? What's that distance? So we have DF distance with AB is 2.5 and E has the distance 3.54. So you take the minimum out of these, which is 2.5. Then distance of DFE with C. So DF with C is 2.24, E with C is 1.41. So you take the minimum out of these two because you are using single linkage and it is going to be 1.41. Okay. Then distance of DFE cluster with DFE is obviously going to be 0. Now what we have is we have three clusters. Now we need to further decrease the number of clusters, that is go from three clusters to two clusters. So now can you tell me what is the minimum value? Obviously the zeros are not included and it is 1.41. That's the minimum that we have. Okay. So now what we will do is we are going to combine the DFE cluster with the C cluster. So now DFE and C is combined. And now we are left with two clusters only. So DFE with C, if they are combined, then what is the distance of DFE C cluster with AB? It is going to be DFE distance with AB is 2.5, C distance is 4.95. You take the minimum out of these because you're using single linkage and it is going to be 2.5. And now we have two clusters. Now, obviously, one step that's left is combine all of them into one cluster. Okay, so this is how it looks like. Now here, obviously, each point is belonging to multiple clusters, so that's hierarchical clustering. And we started with n number of clusters, where n is the number of data points, and then we slowly moved to one cluster. But this diagram does not tell us which two clusters were combined first. It does not tell us which 2 points were the closest and which were combined first. So for that, we have another representation, which is called dendrogram. So let's first write. Let me create one. So the first step was, if you see, first you combined your DF. Okay. Then the second step was you combined your AB. Then the third step was you combined your DFE. Okay. The fourth step was you combined your ABDFE. No, you combined your DFE with C. And the fifth step was you combine your ABDFEC. Okay. So we can make a dendrogram out of it. Okay. So let's see. Let me write the points here A, B. Let me write. Let me write D, F here, then E here, and then C here. You can write it in that order also, but this is going to give me a cleaner dendrogram. That's why I'm writing it in this order. So and basically on the y-axis we are going to have the time. So basically we are going to combine the clusters and the length of the rectangles will keep on increasing and that's going to represent the time. So first let's see. First we combine DF, right? So that's what we do. We combine DF. Then the next step is we combine AB, but we do it at the second step, right? So we make a bigger, basically this is representing the time. So this was done at T1, then this was done at T2. Okay. So this is a bigger time, this is lesser time. Then the next step was we combined DFE. So let me use a different color. Like this. Okay. We combined this at a later point. Then the next step was we combined DFE and C cluster. So at a later point, we did this. Then at a further later point, we combine AB and DFEC cluster. So basically, if you see, this is what is called a dendrogram. Okay. So in dendrogram, what are we essentially doing is we can see which, if you are given this dendrogram and you are told that find out the 2 points which are closest to each other, you know they are DF because they were the first ones to be combined together, right? So there are a lot of things that a dendrogram can tell us. It basically represents the time series in which the clusters were combined and how basically we moved from n number of clusters to one cluster. So this is all about hierarchical clustering. So let's just quickly revise whatever we discussed so far in clustering. So first of all, clustering is an unsupervised learning technique. In that we have two types of clustering mainly. One is called partitional clustering and the next is called hierarchical clustering. In partitional clustering, we discussed k-means, in which what we basically do is we first find out using the elbow method what is the optimal value of k. Optimal value of k means that the inertia is also less and the number of clusters are also less. So we figure out that k, and then based on that k value, we try to figure out the clusters. And the stopping criteria that we have is it could be either of these three. One, you fix the number of iterations and do it for the fixed number of iterations, say 100. Second, the centroids don't change. Or the third is the clusters don't change in the subsequent iterations. And what happens in hierarchical clustering? In hierarchical clustering, we basically have one point which can belong to multiple nested clusters. And the technique that we studied here was agglomerative clustering. So here what we do is we start off with n number of clusters and then we combine them slowly and move to one cluster. And that can be represented using a dendrogram. And here we can have multiple linkages which can be used. The one that we used was single linkage. So that's pretty much about clustering. And we are going to study another unsupervised learning technique in the next class, and then we'll code them together in the final class. So that's pretty much about the course, about this class. Thank you.